Hi and welcome everyone to my talk, Exceptions, the New Spaghetti Code, and how we can rethink error handler in modern software. So a few words about my background. I'm actually a mathematician, so did my PhD in numerical mathematics, and then rather went into the direction of data science. And there, of course, Python is a huge and important language. So I'm mostly familiar with the Python data stack, and I also do a few open source software projects, but mainly Python is my main language, so don't ask me anything outside of Python. And as I mentioned, I work at Innovex. If you're interested in Innovex, we're an IT project center focusing on innovation excellence, and if you want to learn more, please, just speak to me after the talk. But now diving in this little talk, and this is a talk I wanted to give for quite a while because I wanted to kind of make the connections over many different programming languages over the years. So we're going to start really early with the history of goto, and then how exceptions come to exist and what they are actually, what they are used for. And then what newer languages, like for instance Rust, how they rather evolve towards result types that replace exceptions. Then, of course, how can we now apply result types in Python? And in the end, the conclusion to wrap everything up, if you should actually do this. So yeah, starting with the history of goto. So first of all, so I know everyone knows goto, right? Like, if you don't, so goto is just like a really old statement. You jump to a certain label, so you have a one-word transfer of your control flow to another line of code. So to give you a simple example, this is like really old code. It's like one of the first Fortran versions from the year 1957. And yes, those line numbers, you really had to type them. So they're a part of the source code, and this is basically a loop. And this was, the statements if and the statements goto were first introduced there. So you would, in this case, if you would want to square the numbers 1 to 100, you would just increment. You would check if you're already over or equal to 100. You would then jump and say, okay, I'm completed. Otherwise, you jump back to the line 2, and you basically have a simple for loop. And this is how it was done, like really early on. But even nowadays, programming languages like C, it's also already quite an old language, but it also has a goto statement. And it's, for instance, used, let's say in this example, where we want to find something or have a certain condition that is met in some nested loops with variables I and j. And if this condition is true, we want to jump out of both loops at the same time. So we jump to this, to this label end of nested loop. And we will come back to this example many times. So Fortran and which is just a shortcut for formula translation, as I said, introduced goto in the if statement in 1957. And the typical applications, as we've seen, so you skip code, you can use it to loop over code, and you can break out of loops even nowadays, and you can also use it for error handling. So if you don't have any exceptions, for instance, in C, and C is the programming language in the Linux kernel, if you want to clean up something, you after some special condition, you just jump there, clean up, and this also led to the case that in modern, I think I checked it on Linux version 6.12 or so, there's more than 200,000 goto statements in the Linux kernel. And so although we all learn that goto should not be used, there are really good reasons also to use it nowadays, for instance, in C. So as I said, so this is a little history, introduced in 57, and even when C was invented, goto was still kind of a statement that you would introduce in a new programming language. But of course, some controversy about goto also arose over the time, because as we all know, if you use something as flexible and powerful as a goto too much, where you jump around in your code, you get up spaghetti code. And most of you may have used this term already, looking at the colleague's code, saying, well, it looks like spaghetti to me. And this term was actually coined in 1977 by a guy named Guy Levis-Steele. And he, in some paper, which is linked, you will later get also the slides, kind of proclaimed that macaroni is better than spaghetti. Yeah, an American talking about Italian dishes. And so what he meant by macaroni is actually that structured programming, which is kind of the way we are programming nowadays. So to get back to the downsides of gotos, of course, it's hard to understand what's happening if you use it a lot, because you cannot follow the control flow, and this makes it extremely hard to debug. So at that point, then structured programming was a kind of was proclaimed as the alternative, and the goals were to improve the clarity, the quality of the code, to reduce the development time. So same things we are still dealing with today. And at that time, the invention was like the things we now use and take for granted every day, like have proper if-then-else clause, have for loops, have certain block structures, be it with begin or curly braces, or in Python just with an indentation, and also having subroutines. So at that time, this was really new. And with anything new, you first have to prove that the new stuff you're introducing, the new kind of abstraction layer, is as powerful as using goto, right? So this was then done in 1966 by Böhm and Jacobini in their theorem, where they proved, well, so if you can write a program using goto, then you could also write the same program with a structured programming. So not using goto, but only using the just aforementioned control flow statements. And yeah, this was at the time really new. Okay, so kind of get rid of goto and just embrace structured programming. And also then at the time, Dijkstra made a paper where he said that, yeah, well, goto is considered harmful, and that was the time when like everyone was kind of shying away of the goto statement, and especially someone like Dijkstra, so that's the person behind the Dijkstra algorithm, so this root finding algorithm. If he at that time said something like, well, goto is harmful, then of course a lot of persons listened. But then with every like bold statement, there are also people saying, well, really always, is goto really always bad? And Knut, so also an award-winning, surely brilliant inventor, also the inventor of Tech and LaTeX, demonstrated in a paper that in certain cases, actually using a goto can be even more readable, and in a low level can also be way more efficient. And just to get you an idea, even like newer programming languages like Java. So in Java you don't have a goto. It's I think a reserved keyword, but it's not used. you still have a kind of labeled breaks. So in this case, we have again a nested loop with I and j, and we search for some target. And if we found the target, we just save it and we break out of both nested loops by saying, okay, here is a label. So even in Java at a time when goto was still considered or already considered like really bad, they introduced it because in certain cases it really makes sense. So at that point you might ask, so okay, why was goto even like introduced? And why was it introduced in Fortran? And Fortran was really low level at that time, and the lowest level you can go is the CPU and actual machine code, and goto is what the machine does. And like the whole history of inventing new programming languages is nothing more than adding new layers on a cake, because we as humans, we like to abstract, we like to express our ideas in high-level concepts and not in something as low-level as goto. But so we kind of moved away over the time. And as a funny side fact, when there was the break between Python 2 and Python 3, someone also tried to get in those labeled breaks in Python, which was the Python proposal, enhancement proposal 3.1.3.6. And Guido van Rossum himself said, like, no, not with me. And of course, since it's really a democratic process or a controversial process, you can even, it's really interesting to read up those old emails with the people arguing in pro and against introducing those labeled breaks. But this brings us to the question, how do you actually solve now something like this in Python? So now we are seeing the same code again in Python code. You can use, for instance, a state if you want to have this, I want to break out of the outer loop by saying, so if found I and found j are none, and if I set them, I can just check if they are no longer none, and then I break. So this is kind of readable, and it's one way to do it. Then, and yeah, the funny thing is there's a whole Stack Overflow, like really long thread about like thousands ways how to do this, and just a few like special things that I took out of it. So a really smart way for some people is to use the else statement. So how many of you program Python? Maybe just hands up. And how many of you know that there's an else statement behind if, or that there can be? Okay, not still many. Okay. So I think it's like really horrible to read. So what happens here is the else statement is only called if there was no break in the loop. So whenever it was not found, you continue and jump up. But if it was found, then you also break the outer loop, and you also set it then to, so it's really horrible to read, but it's another way to do it. But in this case, you would not want to do it. So to actually get to a way to come to exceptions, you could of course also use exceptions to do this. It's also not a recommended way to do it, but you could raise, if you found the right indices that match the target, you could raise some kind of exception and catch the exception, and by this you also jump out of the outer loop. So definitely not the way to go, but it's possible. And you might ask now, so okay, what's then the actual way to do it? And this was the way then also proposed in the long thread by Guido van Rossum. So you just use a function, right? Because if you put it all in a nice function, you can just return from this function. It's really easy to read. And this was then the point. So we don't need any labeled breaks. So now we have seen that you could also use exceptions to kind of jump around in some cases. Of course, there's something completely different than a goto, but exceptions have similar characteristics. So yeah, before I start, what are exceptions? Surely you have programmed a lot with them. So an exception is an event that breaks kind of the normal control flow and handles edge cases. And those edge cases then require explicit handling, but maybe not where they arose, but somewhere different. So it allows you to kind of separate your code, like the happy success path from the failure path. And this is just a small example where if you ask for a positive number and if it's not positive, you raise this exception and you handle it somewhere else. Okay, this is like really close, but it could be somewhere like up the stack in your program. And yeah, this is the important idea behind exceptions, that they kind of walk down or up the stack. It's like how you see it, rather down the stack. So in this case, let's say we have a function that, so it's really bad code, that reads data, calls some process data, and process data calls some display result, and there is some value error raised. Then this would all travel back down the stack until this point where you then handle this case. So here we also see directly the difference with exceptions. You cannot jump around anywhere, but rather only down the stack. So what about the history now? They were introduced in the early 1980s. ADA was not exactly the first, but like the first like well-known language that introduced it. C++ also introduced exceptions, Java and Python. So like the programming languages that were invented like 25 to 30 years ago kind of all have exceptions for the reason just said. You separate the happy success path from your failure error path, and it's a really nice tool. But it also comes with some problems, right? So if you have ever like debugged a program where some exceptions are thrown, you are kind of have an invisible control flow. You don't know where the exception is actually caught. This might also lead to surprises, especially if you work with a lot of external dependencies and maybe you have forgotten to even to read the documentation, and then you don't have a catch statement or a try statement in Python, and you're completely surprised by the fact that your dependency is in certain cases throwing exceptions. Debugging becomes way more complex. Concurrency and parallelism is a really hard problem, because if certain of your processes die and so on due to exceptions, it's really hard to figure the problems out. And there are some performance issues, although I'm no expert. And in the session of Björn of the keynote, he said actually that this statement is wrong about C++. But at least I know that in the Google best practices in programming C++, they definitely say, last time I checked, that you should not use C++ exceptions due to some performance reasons. So they're discouraged, but yeah, there's a debate about this. And yeah, to sum it up, so we have seen some similarities, but with goto you completely jump to a different line. With exceptions you just go up the stack. So newer programming languages wanted to address this problem. It said like, okay, there are certain downsides to exceptions. Can we do better? And this was the time when result types were invented. And result types, it's actually a really simple concept. Just think of a package, of a container, and you put in this container your actual value that you want to return in a function or some error code. And whenever someone wants to open this container and want to look inside what's in there, you kind of ask, so please also handle the error case. You can enforce it or you cannot enforce it, but in many languages it's then enforced. And this has, of course, a lot of theory behind it. This is the time when we could talk about algebraic data types, about those rules behind them called monadic rules and monads. And if you have if you have attended to any like computer science classes, you've surely heard of them. It's a few important concepts of functional programming. But as I said, I don't want to go down because the actual concepts are really easy. So you just return this package. And now I want to show you how this looks in different languages, newer languages, how they solve this problem, like Golang, which has no exceptions. And in Golang, you would, in a function where you divide something, and of course we have the edge case, we are not allowed to divide by 0. You return always some kind of tuple, and you return the actual value or an error. So if y equals 0, we return some dummy value and the error. And if not, we do the division and return nil, and then we do a safe divide and have a result and an error, and we can check. And this is actually not enforced. So you could also just ignore error, but this is a way how you can do it. And this is then in the end also nothing more than what you would do in C, right? You have kind of special values you return, and this gets you kind of in the same trouble again, like with the in the time where you did not have any exceptions. So now Rust, everyone's talking about Rust, right? So Rust has like a real abstract data type, a real result type with 2 variants. So it's either the float value or the string representing your error. And that means if it's 0, we return error. So this is the variant with a string, or OK and with the actual value. And now here is kind of the magic, so one of the magic things of Rust, that now to get the actual result, you match and unpack the result type, and the compiler would even enforce that you also consider the error path. And this makes it then more robust, because you cannot just ignore the failure and look at the best case, at the happy path. Then there's also Haskell. So you might think, okay, this is something like completely new, but Haskell, and surely a lot of you have seen it in the computer science classes, also had this already in the 90s. Haskell is kind of hard to read, but here you also have this result type, and you do the matching directly here. So if y is 0, you say the variant left division by 0. So this is the unhappy path, and right is the success path. And here, instead of match, you have case, and also left and right. So it looks kind of Rust-like, or rather Rust looks like Haskell. So this has been around for quite a while, and it works in practice. So what do we get now if we use result types? We have no hidden control floor anymore. We have complete explicitness. So we can, for instance, in Rust force that the caller needs to handle this. And that makes the code easier to reason and to reason about the code and to test code. But then again, the downside again is that we now need to handle everything directly. So the clean separation of the happy and the failure path is kind of lost. So uh, now, after this little history lessons in goto exceptions, the question is, can we start now doing this in a language that was never ever intended to have result types like Python? So this was a little side project of me where I was then checking, okay, how could I try this out, and how can I actually really get rid of exceptions in a good way? So not in the way that I just return every time some tuple, for instance, and check it. So what's out there? And there are various libraries. A lot of them no longer maintained, like result o/. The returns library is pretty big, and the expression. And I turned then to the returns library because it's more like Haskell inspired and felt more Pythonic to me. So how would this look like? It's actually quite similar to what we've just seen in Rust. So you have this special result type. You say it's either a float or a string. And if we divide by 0, or if we want to divide by 0, return this failure, and otherwise the success. And then, like you would accept, you get back this result type, so this package with the actual value in it. You can also now, quite often you have external dependencies and or functions that might throw an exception, and how can you now translate them to result types? Therefore is the save keyword. So if this is your function, you don't need to do anything. So it looks completely the same like you would program it. But in this case, save would catch your exception and translate it to a failure, to the failure path. And this is what we see here. If we ask, okay, was there failure? We have the 0 division error as expected. With newer Python versions, newer means like 3.10. You also have the match case as syntax in Python itself. So you could even make it look more like Rust, that you do the unpacking here, the matching and unpacking. And yeah, this is also analogous to Haskell, and you just need to be careful. Sometimes the match case statement behaves kind of strangely in Python. So now we have talked about how we can use it, but how do we now do like the separation of the happy path and the failure path? And there you can do railway-oriented programming, which is just another kind of abstraction layer in your head about how to handle this. And the basic idea is like what we had in our childhood, like those little railway tracks out of wooden that you could just connect to assemble something. And the green path is always the success path, and the red is the failure path. So this component would now represent in my head some kind of function that could go wrong or go well. And with a few building blocks, we could then compose like our whole program. And there are actually not that many building blocks, right? So we can have an operation that goes well or goes wrong. We could also say, okay, if whatever comes out of there, if it did not go well, maybe we want to try an operation that recovers from the failure, if possible, to go back. Then this would be that operation, and then we try another operation, and this whole like packaging and unpackaging we can leave to the framework, and I just start thinking in those components. And we also need a case, what about pure functions? Like what if I just want to have a function that does not have a failure path? There we can just use map. So in this case, I have the success variant with 1. I just add 1 and it's success as seen. and with alt would be the alternative for the failure path, and I would just, if I would apply alt to the success, then it's a no operation. Then we have seen the both components like before. So let's say I have a success, I bind a function that could go wrong, like the divide function that we've seen before. Then if we divide by 2, of course this is possible, then we have a success. Otherwise it's a failure, completely as expected. And if we do the same with a failure state, it just stays the failure. So this is this no operation that's said. And the analogous one is with failure, and this time lash. So this is the recovery from the failure state, the possible recovery. And in this case, I just for sake of simplicity, I check if there's an R in it. In an error, there is an R, so we get a success, and in no, there's no R, so it's a failure. So really simple. And with those 4 components that we have seen, so bind, alt, map, what was it? Bind, alt, map, and lash. We can now start kind of composing all kinds of functions, for instance, with the pipe. And this is now the part where we don't need to, in any function, to always kind of match and unwrap something. We can just compose them. We use a regular function. We use a function that might result in a failure or the actual value. And then, since we have here a function that also takes no container and no result type, but a normal one, we have to kind of make it possible for it to deal with it. So with bind, but then in the end, you just compose it, and you don't need in any of these functions alone kind of do every time this tedious match, unpack, what should happen, should I pass it along or should I handle it here? And this makes it then possible, due to array-oriented programming, to kind of get similar, a similar way of programming that you would normally have the exceptions with the result types, kind of similar. So we've touched only a few points of what returns can do. There's of course a lot more, like containers for I/O, futures, so async calls. Then what to do if you want to deal with resources. So there's managed, then other compositional components besides pipe. And then also things like typical functional things like variadic functions and partial applications. Many of you surely know this func tool partial and curry and uncurry, that you pass along only a few arguments to a function and you get back another function and so on. So a lot of things are implemented in this library that one can try out. Also trampolines for tail call optimization. So if you use a lot of recursion in Python, you've surely noticed that I think it's only a depth of 1000 that is allowed normally. And this you can optimize away in certain kind of recursions. So to come to the to our conclusion, so if you write a program, of course, it's important to not only consider the success path, but also to consider the failure path and make sure to handle it. We have seen like how different programming languages throughout the history introduced result types and how they work conceptually, although we only touched like the surface of it. And we have seen the application of railway-oriented programming to get some of the good points of exception handling also in result types. And we have seen that we can also, in case of result types, we can also enforce, like it's done in Rust and Haskell, that you have to deal with the unhappy path, the failure path. So the question now is, should you use it actually, especially in a language like Python? And as I said, so I tried it out a little bit just out of pure interest of my own. And although I kind of like functional programming, I also did this Haskell when I was at the university, I would not actually recommend it because, yeah, Python is a language like with the exception concept based in it. A lot of dependencies you're going to use will use dependencies. So it might be, if it's not a toy project, but rather something that will go into production, that over-applying some functional paradigm might get you in more trouble than it actually helps you. And still, it might be the right tool for certain use case. If your team, it's also important that depending which team you are working with, that they also like this and like to think functional. I mean, Hobbs is a functional team, but yeah, it's functional programming is a different way of thinking, and result types definitely is a part of functional programming. So yeah, I would say it's really interesting, but maybe not the right thing for production code, especially not in Python. Okay, and with this, I want to say thank you for your attention, and I'm open for questions. Thank you.